Alright, hi everyone. So this is the Unit 9 video. So this is where we were dealing with intermolecular forces, we were dealing with changes of state, etc. So again, as always, pause if you need to at any point, but I'll be working through this. So question 31, for all of these, you were asked to figure out what the dominant inter- or intramolecular force was. So the first step we'd really want to do for all of these is figure out what the Lewis structure would look like, and even if you can draw one. If you can't draw one, that's a good sign that you're probably dealing with an intra rather than an intermolecular force. So I'm going to sketch those out really quickly. Okay, I already went over, I should say, the rules for drawing Lewis structures in the Unit 7 video, so if you need to take a look back there as a refresher, please do. I'm also going to draw them in 3D. You don't necessarily have to, but I do think that helps sometimes figuring out what the polarity is. This one I'll draw flat just because we're going to have two central atoms, so that'll be a little bit tricky. Alright, here's the other one on this page. Oops, I forgot I was drawing that in 3D. Let me reset that really quickly. There we go. So there's the ones on those page, and here's the one on this page. Now, NaCl, if you try to draw a Lewis structure for this one, you can't really draw one. The reason being, this thing is ionic. We have a metal and a nonmetal, so that'll be important later. SiO2, we can draw a Lewis structure for, so we'll draw one for that. But I'll talk a little bit more about this one in a moment. Actually, let me do this one from scratch. I'm going to come back to that one at the end, and we'll talk about why. Mg, single element, so we can't really draw a Lewis structure for that one either. And then last but not least, we have HF, which would look like that. Okay, so we have our Lewis structures. Why did I draw the Lewis structures first? For the things that we could draw Lewis structures for, the molecular compounds, we discussed there are three kinds of intermolecular forces. There are dispersion forces, also known as London dispersion forces, which are in everything. There are dipole-dipole forces, which are only in polar things. And then there are hydrogen bonds, which show up in both polar molecules that have a hydrogen specifically attached to a fluorine, an oxygen, or a nitrogen, three very electronegative elements. Okay? So if I look at all the covalent ones first, I know they all have dispersion forces, okay? But it's asking for the dominant one. So if we're looking at the order of importance, if we list them up at the top here, dispersion forces would be the least important, dipole-dipole forces would be a little bit stronger, and then your hydrogen bonds would be the strongest of the intermolecular forces, inter meaning between different molecules, okay? So if we're looking for the dominant one, for all the molecular substances I just drew Lewis structures for, we'll figure out which one of these three are present, and then we'll pick the dominant one. So for A, this thing is nonpolar. Okay, so I'm going to jot that off to the side. This thing is nonpolar, so it definitely has dispersion forces. It does not have dipole-dipole. It also does not qualify for hydrogen bonding because boron is not one of the Fon elements. So this thing, the dominant intermolecular force, would be the dispersion forces. Remember, these are temporary dipoles. Okay. B, this thing is also nonpolar, because everything attached to the center is the same. So again, this one would have dispersion forces as the dominant or strongest intermolecular force. Okay. Methanol down here, this one is polar, because this OH down here at the end is unique. I'm pulling a little bit differently. So this thing has dispersion forces. It also has dipole-dipole forces, and it has hydrogen bonding because of this H attached to an O down there. So in this case, hydrogen bonds would be the dominant intermolecular force. PCl3, this thing is polar because of that lone pair of electrons right there. No hydrogen to be spoken for, so this would have dipole-dipole forces as the dominant IMF. Alright, so there's the first couple. Now moving on to the next few. There are a bunch on here we can't really draw Lewis structures for. So the only one we drew a Lewis structure for was this one at the bottom, HF. Okay? If we think about this one, it definitely has dispersion forces. This thing is also polar because of the difference in hydrogen and fluorine. It also would qualify for hydrogen bonding because we have an H attached to an F. So hydrogen bonding would be the dominant one there. Now for the other three, we didn't draw Lewis structures. So if we think back to our solids unit, we had a couple different kinds. We had ionic solids, we had molecular, we had network covalent, we had metallic, and we talked about amorphous briefly. So I'll start with NaCl. NaCl is ionic, so this one doesn't actually have intermolecular forces. This is actually held together with intramolecular forces. In particular, if you think of those solid types, the intramolecular force here would be ionic bonding. How do you know it was ionic bonding? Because you have a metal and a non-metal in that formula. Okay? Intramolecular forces are always way stronger than inter, so this salt would have a way higher melting and boiling point than any of the ones we did from A through D. Okay? Now, SiO2, you can technically draw a Lewis structure for this one, so I did start doing it and then I erased it. The reason being, when we thought about our network covalent solids, we said generally they were harder to define, but what you were looking for was usually a group 14 element that makes really strong bonds arranged in these large macromolecules. And SiO2 is one of the examples of a compound involving a unit 14 element, silicon, that qualifies for there. So this one actually does qualify as a network covalent solid. Alright, so what we have going on are lots and lots of covalent bonds sort of holding this whole thing together. Okay, so this is a unique one. You could have argued that this would be covalent bonds as the dominant intramolecular force, but if you chose to draw a Lewis structure for this, you could say that this thing is nonpolar and say it has dispersion forces as well. So depending on how you approach that one, you could really go either way. The last one on here was G, magnesium. So we did not draw a Lewis structure for this one because it's a single element. So again, if we think about those 5 solid types, which one are we most likely to see there? This is definitely not ionic because it's not a compound. It's not molecular because, again, not a compound. What we have is a single element that's a metal, which means this is a metallic solid. So once again, we have an intramolecular force. We have metallic bonding as the most important intramolecular force there. So again, this is an inter, this would be intramolecular. Okay? So there's a quick overview of inter versus intra and how we approach all those. Now moving to 32, it says to discuss the differences between different types of intermolecular forces. I've kind of already mentioned these here and there. The strength of the forces would be the same thing I listed on the top of the last question. So our dispersion forces would be the weakest. So I'm just going to abbreviate, but like I mentioned in class, please make sure you know what that actually stands for. London dispersion forces. Dipole-dipole forces would be a little bit stronger because these are permanent dipoles, whereas dispersion forces are temporary. And your hydrogen bonds would be next. Now, again, this only asks about intermolecular forces, but keep in mind that all 3 of these are very weak compared to intramolecular forces. So I'm just going to jot that off to the side here. So very weak compared to intra, such as ionic bonding, metallic bonding, etc. Okay? And then with our melting and boiling points, the more forces that are holding the molecules and atoms together, the harder it's going to be to make those atoms and molecules separate and change phase. So we can say that the more IMFs there are, so the more intermolecular forces / the stronger the forces, the higher the melting and boiling points will be. So things that have all 3 intermolecular forces have a lot higher boiling points than things that only have dispersion forces and so forth. Okay? 33 sort of summarizes some of those solid types that I mentioned before. So once again, feel free to check these out. Rather than me filling them in all by hand, I'm going to take a picture of it and overlay it. So just give it just a sec. Alright, so here's a copy of that chart. Feel free to pause if you need to fill anything in. Just a quick overview of what's in here. So metallic bonds, we talked about that sea of mobile electrons, that key that they were delocalized. So the electrons are not tied to any one particular atom. They have a lot more freedom to move around. Your network covalent solids, we probably shouldn't have grouped these 2 together, but network covalent solids, you have covalent bonds between all the molecules. The difference between a molecular and a network covalent substance is that molecular, there are covalent bonds between the atoms in one molecule, but then the other molecules are held together via intermolecular forces. In a network covalent solid, it's just an entire system of covalent bonds, so IMFs don't really come into play. For ionic solids, you have a cation and an anion. Cations are generally metals, anions are generally nonmetals, but you can have polyatomic ions as well. Notice that as far as conductivity goes, metals always conduct electricity, but ionic things only do when they are dissolved. So that says aqueous, even though it got a little bit cut off there. Okay, so they only dissolve electricity when they're dissolved in water or molten. Okay, generally your ionic ones are the only really soluble things here. Some keywords for metals: that term malleable. We saw that before. We also see the word ductile applying with metals, so you see those two down there. Okay, so if you did not do very well in the solids section of our Unit 9 test, I suggest you take a look back at those as well, but that was sort of a quick overview. Moving to question 34, we're looking at our vapor pressure curve. So you have this curve in there, so we'll just go through each question here. Quick word about the axes. Up the side we have vapor pressure, which again is the pressure of a gas over a liquid. So the more a gas evaporates, the higher the vapor pressure will be. And then we have temperature across the x-axis there. So part A says, at what temperature does CCl4 have a vapor pressure of 60 kPa? So we're really just reading the graph at this point. So if we find CCl4, it's this line. So if we see here 60 kPa, if we trace that over, the question is, what temperature is that happening at? I'd say it's just over 60. So feel free to approximate a little bit differently, but I'd say about 62 degrees Celsius. Make sure you put a unit on your answer. For part B, it says, what temperature is the normal boiling point of CCl4? So remember, the normal boiling point is where, well, let me start here. The boiling point is where the vapor pressure and atmospheric pressure intersect. Okay? The normal boiling point is based on standard pressure, so 1 atm. So what we're looking for is the intersection of 1 atmosphere of pressure, which would be equal to 101.3 kPa. That's why you see it marked there. And the vapor pressure. So where do those two lines intersect for CCl4? Here's that 101.3. Here's the vapor pressure. So again, if we just trace that down to the temperature, that'd be right around 75 degrees Celsius. All right. And then our last one, at what pressure does CHCl3 have a boiling point of 30? So again, it doesn't say normal boiling point, so it's asking where would the vapor pressure, basically at 30 degrees, where does the vapor pressure intersect with atmospheric pressure? Okay, so if we go to 30 degrees, right here, we are going up to the CHCl3 line, which is right there. So here's the vapor pressure, right? But if we trace that over, that also means that would be approximately where our atmospheric pressure must be to make this thing boil. So if we approximate that, I'd say around 33 kPa. Remember, kPa are kilopascals. Okay, so there's a quick overview of our vapor pressure curves. There were some other questions we asked with these as well. So again, as always, check out your notes and old homeworks. Okay, this next one, this was the lengthy one from this unit. So I'll try and go through it quickly, but make sure we hit all the pieces as well. So, if you read this fast, it sounds like we could just do it with one equation, Q equals mc delta T, because you see temperature, you see mass, you see specific heats, right? But, if you remember, we tried to sketch out some cooling curves and heating curves and stuff for this, right? So, if we sketch that quickly off to the side here, generally, it looked like roughly like that. So we're heating it from -4 to 100. It's talking about water, which we know that the boiling point for water is 100 degrees Celsius. So I'm going to mark that right there. And we know that the freezing point is 0. So I'm going to mark that there. Okay. So if we are starting at -4, that's down here, and we're going up to 110, that's approximately there. So if we count how many pieces we need to do 1, 2, 3, 4, 5. There are 5 segments in this graph, which means we need 5 different calculations. Okay. Now remember we mentioned that there were 2 equations we use. Anytime you have a slant or a diagonal, you're using Q equals mc delta T, because only on the diagonals is the temperature changing. Anywhere you have a phase change, so those will be on the plateaus, there and there, we use this equation, Q equals N delta H, and the delta H would correspond to either vaporization or condensation or boiling or melting, depending on what you were doing. Okay? So we're going to have 5 different equations here. The biggest thing to keep in mind is that you have to pay attention to that you're using the correct unit, not the correct unit, the correct constants, and the correct temperature changes when appropriate. Okay, so starting with phase 1 here, let me just number these quickly. So this would be step 1, step 2, step 3, step 4, step 5. Okay, so starting with step 1. Step 1, we are on a diagonal, so we're using the temperature change equation, Q equals mc delta T. So we're solving for the energy change during all this, right? Because it said calculate the amount of energy. So what was the mass? If you look in the problem, it said that the mass of this sample was 5 grams. So I'm going to plug that in. As far as our C value goes, we're dealing with, if we're under 0 degrees, water is frozen, right? So we're looking at that point at solid water, or in other words, ice. So I'll plug in that with this compound unit. And our temperature change. Here's the thing to keep in mind. Temperature change, delta T, remember, is always final minus initial. And we're not using this whole thing, so you don't just want to plug in 110 and 4. All you're doing in this first segment is going from negative 4 to 0. So that's only a temperature change of 4 degrees. Okay? Or if we plug it into our formula, so if you don't want to think about it that way, final temperature being 0 degrees, the original one being negative 4 degrees. Which, again, if we add a positive there, that's going to be 4 degrees. Okay? So, if you check your units, notice that grams cancel, Celsius will cancel, leaving you with joules. Okay? So if we get our answer for that first segment, we'll see that this comes out to about 41.8 joules. Okay? So there's step 1. Step 2. Step 2, if we look at our graph, is a plateau. This is a phase change. So we're dealing with Q equals N delta H. The question is, what phase change is happening there? At 0 degrees, if you're heating it up, this would be melting, which is also known as fusion. Okay, so before we can plug our values in there, the first thing you have to recognize is that N is not mass, N is moles, but it was given us a mass in the problem. So up at the top here, I'm just going to do a quick conversion here, so we can convert our mass to moles. So we have 5 grams of ice, which is water, right? So if we take that and we use our molar mass, the fact that 1 mole weighs about 18.02 grams, this means we have about 0.277 moles of water. So even though it's an extra step we have to do, it's the same mole value for both of the phase change steps. Okay? So if we go back to our math down here, now we can plug things in. So we have our mole value. And then if we look over at our constants, delta H of fusion, you see it right here, 6.01 kilojoules per mole. If we look at the units, moles and moles cancel, leaving you with kilojoules, which if you're thinking ahead here, you're going to recognize that we're going to have a discrepancy with the units. Because this one comes out in kilojoules, but this one came out in joules. So when we add all these together, you're going to have to account for that. I usually change the joules to kilojoules, but it's up to you which one you prefer to do. So if I do that up with the first one, thinking back to our metric prefixes, there are 1,000 joules in 1 kilojoule, so that would make this 0.0418 kilojoules. Okay, so there's the total for step 1. Here's our total for step 2. Oops. All right. So if we now move on to step 3. So step 3, we're back to a temperature change again. So we're going back to this equation. Okay, so plug that in. Same mass, still 5 grams total for the sample. Now it's a different specific heat value though, because we're talking about a liquid in this middle section here, right? In here between 0 and 100, water is a liquid. So now we're using this specific heat. We normally just did 4.18 before, but if you use 4.184, that's fine. It's just being a little bit more precise. As long as you show your work, I'll be able to follow what you did. The temperature change for that segment, we started at 0 degrees and went all the way up to 100. So final minus initial will give you a change of 100 degrees. Okay. So if we do our math there, we would get 2,092 joules. But just like we saw in the previous one, I'm just going to change this to kilojoules right now, just to save us some time at the end, also so you don't forget. Alright, so there's step 3. Okay. step 4, we're back to a phase change again. So we'll go Q equals N delta H. At this point, once you get to 100 degrees, water is boiling, which is better known as vaporization or evaporation, but vaporization is the one that they usually label the constant with. So if I plug in here, the mole value will be the same as it was from step 2. Delta H of vaporization, if you look in the chart, is 40.67 kilojoules per mole. Once again, we see the moles canceling, leaving us with kilojoules. So for this 4th step, this would take about 11.28 kilojoules to melt that whole, to boil or evaporate that whole sample. Okay, so we're almost there. This is as long as we could potentially make it. Okay, so for our last step, step 5, let's see, we'll go with, alright, so for step 5, the last part, you're heating it up again. So we're back to Q equals MC delta T. Alright, so the mass, still 5 grams. The specific heat capacity is the specific heat capacity for gaseous water. And our temperature change, again, if we do final minus initial, we were at 100 degrees, and we went all the way up to 110 degrees. So that would be final minus initial, which would give us a change of 10 degrees overall. So if we do all the math for that 5th step, you would get 92 joules, which once again, if we convert that, will give you 0.092 kilojoules. So you can see that most of the energy is going into the phase change sections, not the heating up sections. Okay. But our last and final step here needs to be to add up everything up, right? We have 5 different answers here. So if we add all of the final steps here from all the other mini problems, essentially, we get that Q total would be the sum of all these. So our answer from step 1, our answer from step 2, our answer from step 3, step 4, step 5. If we add all of that up, as far as sig figs go, you could look at this a couple ways. So if you did 2 sig figs, because 4.0, that's fine. Technically, we have addition going on in here, so we probably should have been paying attention to decimal places, but I won't be too much of a stickler about this at that point. So all in all, I'd say you'd get about 15 kilojoules. So you'd need about 15 kilojoules of energy to make this whole phase change happen there. All right? So that was quite a long one, but there's our whole phase change calculations. Again, if you weren't good at these back in Unit 9, I suggest you go and take a look at them. All right, our last question, this one's much easier compared to the last one. It says sketch a heating curve for water and label all phases and energy changes. So we sort of just did this in the last one, but it would look roughly like this. So there's our axis. Across the bottom we have time. Going up the side we would have temperature, which of course we know would need a unit of some kind. Okay. Let's see, our steps would look roughly like that, with our temperatures labeled over on the side. I probably should have written that a little bit farther away, but that would be about 0. This plateau would be about 100. Okay, and it also told us to label all of the phase changes, right? So here would be heating up just a solid. Once we get to this point right there, there would be our first phase change. You're going from a solid to a liquid, which would be melting or fusion. Okay. If this were cooling, that would be where freezing would happen. Okay. Then you would heat up just the liquid. Once you got to this segment, would be our other phase change. So you'd be going from a liquid to a gas, which has a bunch of names. You could say boiling, you could say evaporation, you could say vaporization. They all mean the same thing. Vaporization is the one they usually use with the constant, though. Okay. If this were a cooling curve, the mirror image of this, at that plateau you would have condensation occurring. And then your last step, you're just heating up a gas. Okay, so there's a rough heating curve showing all phase changes and energy changes there. Okay, so that was our Unit 9. Next video, we'll be dealing with Unit 10, which was solutions.